Weighted majority algorithm is a sublinear regret algorithm which fully utilizes the randomization technique. Weighted majority algorithm or randomized algorithm with experts. So there are n different experts indexed from 1 to d. And each expert independently learns some prediction algorithm rule. And this weighted majority rule just learns some coin tossing with some probability, and then from the just random coin tossing, randomly select one of expert at each time, and then just follow the expert advice. Okay. At each time, randomly choose expert I more precisely with probability WIT, and then follow the advice of the expert I, and then receive YT, the true ground truth YT, or directly receive a cost vector VT that define the regret or loss of each expert. So VT is d-dimensional vector. All value will be in between 0 and 1. And each element represents the loss or cost when we follow each expert. And then update WT plus 1 for the next trial. And then how can we update WT, the probability vector? First, the probability vector is proportional to double tilde parameter. This denominator term is just normalizing factor, so that WT becomes a probability vector, non-negative, and sum of all the elements equal to 1. So we just divide by the sum of element. And W tilde T follow this updating rule. So starting from value 1, and at each time we multiply for each element, we multiply exponential minus eta times the cost VTI, cost of expert I. Then here eta is kind of learning step size, or the learning rate or step size, right? So it's common parameter in many machine learning techniques. Then from the exponential property, basically W tilde I t plus 1 is equal to exponential minus eta summation from t1 to from I equal to 1 to, no, I'll use different notation, from j1 to t v j I. Okay, so that is W tilde I t plus 1. So exponential minus step size times sum of all the costs up to time t for each expert I. So intuitively, the W vector, the W probability vector, proportional to exponential minus sum of cost minus step size times cumulative cost from time 1 to time t. So when an expert I has high cost up to now, then it is reasonable to give very low probability, low chance to pick the expert I. Because up to now, from the history record, we know that this expert incur high cost. On the other hand, if the cumulative cost up to now is very tiny, then it is good to pick more frequently, more often, the expert to reduce the regret. So that simple rule we apply for weighted majority. Okay, and this simple rule works very well when capital T, the end time, is greater than 2 times log D, and the step size is equal to square root 2 log D over capital T. The weighted majority algorithm has the regret bound, this, square root 2 T log D. So this is sublinear regret. When you divide by T, this value converts to 0 as capital T goes to infinity. The regret does not grow linearly to capital T, but increase with speed of square root 2 T. So this is much better algorithm than any deterministic rule for the adversary attack. The proof is not so difficult. We can understand. So that basically use kind of potential function technique. So instead of directly attack the regret, we will find upper bound and lower bound of a potential function, and then using the upper and lower bound, we can conclude the regret. Then what is the potential function? The potential function is the denominator term, the normalizing factor for the WT vector. So ZT, let ZT is equal to sum of W tilde T. Okay, the normalizing factor to define W probability vector. So by studying ZT, we can obtain the regret upper bound. Right, so from the definition, we have this information. Log ZT plus 1 over ZT is equal to this. More precisely, actually, the potential function is not the pure ZT, but log ZT. Okay, so we will study the upper and lower bound of log ZT, and from the upper and lower bound, we can conclude the regret. So from the definition of ZT, we know that ZT plus 1 over ZT has this property, right? Because W tilde T updated as follows. W tilde T plus 1 is W tilde T times exponential minus eta times the cost. Okay. And using the fact that W tilde over ZT is equal to WT, so we can rewrite this as this. And this is upper bounded by this because of this factor. Exponential minus a is less than or equal to 1 minus a plus a squared over 2 when a in between 0 and 1. And we know that Vti is in between 0 and 1. And we also know that eta is very tiny. We know that eta times Vti is in between 0 and 1. So using that fact and this inequality, we have this. Okay. So when you use the fact that Wi is probability vector, the sum of Wit is equal to 1, and then we can rewrite this. And since log 1 plus x is less than or equal to x, for all x greater than minus 1. So this is very useful inequality. Log 1 plus x is less than or equal to x. Then the equality is hold when x is equal to 0. This is very basic inequality. So using this fact, we can remove log term and just write down this term like this. So we can rewrite this part as an inner product. So eta times inner product between WT and VT, the selection probability and the cost, plus eta square summation I from 1 to d WIT times VTI square over 2. Okay. And since the cost value always in between 0 and 1, we can simply upper bound this by this. Therefore, when you sum up this term from T1 to capital T, we have log G capital T plus 1 over G1. This is equal to the summation log G T plus 1 over G2 T from 1 to capital T. This is upper bound by summation over this from T1 to capital T. So we then find the lower bound of log gt plus 1. Since w tilde t plus 1 is exponential minus step size eta times the cumulative cost, so this is equal to this by definition. And one very simple and powerful trick is summation can be lower bounded by max, right? So when all the element is non-negative. So using that inequality, we have this bound. And this one, by definition, we can cancel out log and exponential, and since there is minus, we can rewrite this term as this minus eta times minimum of summation T1 to capital T VTI, minimum of cumulative cost. So from the upper and lower bound, what we obtained up to now, so we have this. This is the lower bound of log gt plus 1. So write log d here. From the definition, log g1 is equal to log d. So this is the lower bound of log gt plus 1, and this is upper bound of log gt plus 1. Okay, so which can be rearranged as follow. And this is the cumulative expected cost by algorithm A. And this is the best possible cost, the best minimum cost by one single hypothesis, by one single expert. Okay, so this is the regret with respect to expert set, and the regret is upper bounded by this. So when we optimize the step size eta, we finally conclude the theorem.